And when I tried that one, it wouldn't plate solve because it was so vignetted that it just had a little hole in the center of the field.
Mhm.
And that's okay for speckle, but it's not okay for plate solving. But I got a 2-inch Barlow, and now its field is bigger than the vertical part of the camera, but limited on the edges, on the sides, but not too badly. And it plate solves every field I've found. So that's
No
great.
kidding. That's
Yeah.
great. Okay.
So
Good news.
and that's at I don't know, with the 6200 camera, it's about f20 or so, somewhere in there.
That's
I
an
don't remember.
excellent magnification if you want to do, G band. You probably don't, if you want to do R band, probably f15 is good enough.
Yeah.
But, with that camera,
Well, I
That's
do all
what,
4 of them, and it's probably overkill a little bit. The other thing was, the other question I had, which I don't think has an answer. I've never done calibration of images, of speckle images before, and I understand how to do calibration of full frames like we're talking about for precision astrometry, but I've never figured out a way to do calibration of speckle frames because the ROI might be anywhere in the field, and you have to register the camera pixel by pixel in order to do proper dark, let alone flat fielding, but dark and well, any kind of calibration. And I don't understand any way to be sure that you're registered properly. Is there any ideas on how to do that?
So let me first say that I've tried dark subtraction, and it doesn't improve much at all. And
Yeah, I've tried it too, and it doesn't.
the reason is that the dark noise is swamped by the other noise sort, the atmospheric noise. So, and when you process it in the Fourier domain. So every dark photon that you got gets spread over the entire spatial frequency domain. And then if you use the trick of removing the photon bias, which is basically the reason that you do it, then you've excluded a lot of it anyway, and so forth. So in my tests, and I did quite a few tests on a couple of different systems, and I found almost no difference between dark subtracted and not dark subtracted. So I don't really think it helps, Rick. So
yeah, that was my conclusion too, except that some of the so-called quasi speckle images that are, for really faint stars in the band where they don't shine very brightly, the exposures are up to maybe several seconds, and even there I think it would be helpful to dark subtract, but I still don't see a way to do it. And I think the cameras now are so good that it really is less and less necessary all the time because the dark noise is so small.
The new CMOS camera.
Can't flat fielding help a bit, or are you doing flat fielding?
No, I'm not doing it, and I don't know how to register that either. In a speckle ROI.
Flat fielding will only increase the noise by a little bit. It doesn't help this problem at all.
It's good.
It certainly helps if you're doing photometry over a wide field of view where your comp stars are spread over a wide field of view. It's certainly necessary to flat field, but that's only going to add a little bit of noise depending on how good your flats are. So I don't think, Rick, it's important at all.
Yeah, that's my conclusion too. I didn't know in the first place how you would ever register it, and the second place, it doesn't matter.
Right. It certainly
Rick,
doesn't
I've got a couple of questions. What software are you using to make the observations, and what are you observing?
I'm using ZWO cam, same as Firo and Barrow use, except that I'm not using it connected to the telescope because they don't have they prefer not to have a connection. So I'm acquiring the data on my laptop, and the observatory computer is running the telescope. So I got to go back and forth between the two. But that's really no issue, except there's a couple of nice things that you can, tell the telescope to guide, just keep things centered and stuff like that. But so I have to use a hand paddle, but that's okay. It's just necessary to keep the human in the loop instead of the software.
And what
Um,
are you observing?
I'm observing stars with known orbits or predicted orbits, but not having spectral types for both components. So I'm trying to do what that paper was about, to try and estimate the spectral types of the individual components, which apparently have never been observed before.
Great, yeah, thanks.
They all seem to be bright stars. There's very few that are fainter than like 10th magnitude. That's kind of surprising. I don't know why that is, unless maybe most of them are, bright double-lined stars that are easy to take a spectra of and tell what the two components are. Maybe that's where most of them came from. The ones that are known, most of the 90% of them, 99% of them are not known. They just have one general spectral class, like this is a G0 star. Well, yeah, plus or minus one whole spectral type probably, let alone the components.
Yeah. I have a
Anyway.
couple of questions. Sophia writes, I'm not sure if you're still working on the plate solve problem, but I encountered this when looking through some coding things, and it might be a method.
It's
Sophia?
a software thing that to help you write web apps, basically. You can add it to any Python code, and then it'll make a web-based server for it. So if there's a way to kind of convert the current code into something with Python, you should be able to use that to make it a web app.
I have quite a handful of people that are asking me to write stuff in Python now, becoming the Tom shaking. Yeah. And so I don't know what to do. I don't know whether to get into it or not, but I have to think about that seriously, because well, what anybody else have an opinion about that?
Yeah,
It's a
yeah,
lot of
Dave,
work.
I've got a little opinion on that, if you don't mind. It
Yeah.
seems like all the even professional astronomical packages right now have been written in Python to work with those particular data sets you're dealing with. And that's the way the professional community is actually moving, which is kind of surprising. I don't know if you remember or not when we had that run at Kid Peak, and what was that fellow's name, Russ, that kid's name that was going to do all the Python programming for us? Do you remember?
You're muted.
You're muted.
I know who you're talking about. I don't remember his name.
Yeah. Anyway, he was kind of in the lead, really. I mean, he saw what was going on, and there are so many astronomical packages currently developed for Python that you'd be kind of silly not to, because it's such a fast, easy, iterable kind of a language for developing any kind of code you want. You don't have to go through the compile and make formats and all that kind of stuff. It's interpreted, so you just run it. And it's really worthwhile is what I'm trying to tell you, Dave.
Yeah, and Microsoft makes an IDE for it. It's the same IDE. It's the Visual Studio IDE, and they actually added Python to it about a year ago. So
Guido van Rossum also moved over there to do some work with them on their implementation. So it's got a backing.
yeah, it's become the thing to do, I think, for this type of work. So I guess it's going to be hard to avoid unless I really feel like I can't do it anymore. It does take a certain amount of oxygen to the brain. And
Well, a
when
suggestion
you
for
do,
you, Dave, to get started, a suggestion is go to anaconda.org and download the Anaconda install, because it brings with it all the packages you need, AstroPi, it brings NumPy, it brings SciPy, all the good packages you need to do any kind of scientific processing.
can you write that in the chat and I'll
Sure.
take a look? Give me a link or something. Well, okay, maybe I'll take a look. I won't make any more jokes about it. I'll seriously take a look and see what I should do. Thanks, Sophia. You know, it probably is time to move away from the way I'm doing this clunky work now and get into something better. So, anybody else have a question? Let me see. Calais says, yeah, right. I agree. Some students love it. Some others hate it. Well, what I've looked at it a little bit, and it's pretty close to C and to, I mean, the way that you use it, it's an object-oriented programming language. So, you know, if you understand how that works, it's really no different. The syntax is a little different, and that's it. So really, I think I could probably come up to speed if I have a kind of a good reference in front of me for it. I'll probably buy a hard copy book because it's kind of easier to read a book first to get into it, because then you see the tricks and the structure and then jump into it, and I'll see what I can do. I'd love to make PlateSolve a Python program. And it looks like in the Visual Studio IDE, I can actually take modules from C# and from Visual Basic and actually run them in Python. It appears that's my understanding, but we'll see. Yeah. Okay. Anyway, thanks. I'll take a look, and maybe that'll be a little bit of work I do here while I'm in Colombia. I'll be here until the first week of October.
Dave, are you familiar with Lisp, the language Lisp?
Yeah, I used to write in Lisp. I
Well,
loved it.
Python, believe it or not, Python and Guido actually developed around Lisp. So you're going to see an awful lot of that same kind of syntax and methodologies implied.
Yeah, Lisp has quite a different structure in the way that things are computed. So, okay. So for the next few weeks, I guess what, 7 weeks? Is it okay if we have it at this time on Thursday? Does it work for everybody? Okay.
I think it works for
Everybody-
this. I think it works for this group, but people like Leon, I think it's way, I don't know if the timing, he couldn't make it. I know that. And
Yeah, it
maybe
would
the
be
Hawaii
dinner.
people can't make it. I don't know. It's real early for Hawaii. I'll find out. Maybe Leon can make it. He just couldn't make it today.
Leon is in Germany, so he's what, 8 or 9
It's probably 6 hours from you.
6 hours from me.
Yeah.
Well, I'll talk to Leon. Leon and I chat quite a bit. He's working. So an interesting problem, I don't know if he's told you or not, but he bought a 10-inch Cassegrain from GSO, the manufacturer. And we were trying to take flats, right? So he took a flat, and instead of seeing the normal vignetting pattern, which is at the edges, you know, you have less light, he saw more light. And I immediately knew what that was. It was incorrectly baffled Cassegrain. So he's getting skylight around the baffles. And we did a little bit more analysis, and he only has a kind of a really small field of view that's fully baffled, unfortunately. So they screwed up the baffle design pretty terribly. I mean, it's only 10 or 12 millimeters fully baffled. So it's a horrible design. And this is a telescope that costs a substantial amount of money. I mean, it's not a toy. It's a $3,000 telescope or something. So, you know, that's really unfortunate. But Leon has a 3D printer and we're trying to get an optical drawing from the manufacturer, from GSO. And if we can get that, we can design our own baffles and he can 3D print them. And so he's going to have, for instance, that'll give you terrible trouble if you try to do photometry and you want to use a photometric field that's larger than 10 millimeters. You actually really can't do it. You get the wrong answer. So if you're trying to do millimag photometry, you're hopelessly screwed by that telescope. Okay, so that's just an interesting side. You got to be careful of your equipment too. Let's talk about calibration since we arrived there. Let me start again. Uh-oh, you've disabled screen
Oh,
share.
yeah, I'm sorry. Do that. Yeah, there you go. Okay, now you got it.
Yeah, okay. So I suppose actually everybody knows most of this already. I don't know if this is really a good thing to do. You guys tell me. You think this is a good thing to do right now, or should I do it with?
Yes, please.
Okay.
It can be brief, but it would really be super, super helpful for me if you wouldn't mind.
Okay, so let's start with what we get from an image. The image, and this of course is XY. This is pixel by pixel. I won't write all of that stuff because it's too hard to write already. The image is composed of the bias. There's a bias in every camera. We'll have some bias and it will have some dark current. We'll call that D times the exposure time T, right? Because the dark current just accumulates photoelectrons that you don't really want. And now there's an overall optical, so that's kind of the stuff that the camera produces all by itself. And we certainly don't want that junk. Now, what else does the camera see? Well, it could actually see stray light. So like in Leon's case, so it could actually see stray light, but I should have, is there an eraser in this thing? Yeah, there is. So, how lovely. Okay, format. What am I doing? Draw? No. How do I get back to the, no, draw, stamp, eraser, format, line width. I want to get back to the pencil. How do I do, where's the pencil?
I've never used it. I don't know myself.
Am I in pencil mode? No. Draw a line. I suppose that is that.
There you go.
Well,
That's a line.
Line. Okay. I have to explore the tool first here. Draw a squiggly. There we go. Got it.
B was the background
B is the bias.
bias. And the bias is the degree to which a pixel,
So this is just, this stuff is the camera.
yeah, okay, camera.
The bias is just the whatever comes out of the camera with no exposure, zero exposure.
Right, that's right. I remember that from last time, got it.
Now, there's going to be a bunch of photons that come into the camera from the outside world. And so there's going to be a gain function. And this gain could depend on wavelength and, well, wavelength is the only thing I can think of, but there's a gain which converts photons into photoelectrons, right? So the gain times, and now there's a bunch of ways that photons can get into the camera. So these are now photons. So this is going to be all be photons. So what are all the ways that photons can get into the camera? Well, they can get in through stray light, just directly from some source of light that you don't want. So that's going to be part of the background that you want to eventually get rid of, right? This is the stuff that didn't even come through the optical system. And then, right, we've got the optical system, but the optical system has an optical transfer function, which I'll call what? O for optics. And then O. And now this is the stuff that came in from the outside world, right? This actually came through the optical system. You got it? This is just stray light, just stuff that you didn't even go through the optics. It came into the camera from some other way, like around your baffles. This is what Leon's facing.
Right.
Okay.
Is gain part of the camera as well, or is
Seeing?
the gain, the G parameter, that is
Yeah.
should that be sort of under the camera umbrella?
This is electrons per photon.
And the camera controls that's like the quantum efficiency or something?
That's what we call the QE.
Okay.
And it's a function of wavelength, which I should have written in here, but it gets a little bit complicated if I.
Got it. Thanks.
So now we have the stray light, which often we don't even think about, but it's there, right? That's just stuff that got in. This is the optical transfer function. In other words, if I have that goes through the telescope. So the rest of this stuff, these are going to be photons that made it through the telescope. And what stuff is that? Well, there's background, they're just sky glow, right? Which we call, I've already used B, I'll make it BG. So there's background, which is a function of wavelength and maybe even position on your sensor, because the background, there can be a gradient, fairly complicated stuff, but there's a background. And then there's the actual object that you're trying to, then there's the actual field of stars or the nebula, and we'll call that OB for objects. And this is the stuff you want. That's the only thing that you want. You actually want to get rid of all of the rest of this. And the process of, you want to get rid of this, you want to get rid of this, you want to get rid of this, thing and so forth. So you want to get rid of everything you can and just leave the object photons. And of course, this is a function of lambda. And it's a function of the position XY on the frame. Okay, so to explore this and this guy a little bit further, and this guy, let's talk about all of this. This is the OTA. My nomenclature here is, not very good, but let's work backwards now through this thing. So what does this function look like? If this is X or Y, this is the radial, this is Rowe, the radial position from the center of the field of view. Well, telescope's vignette, so this thing is going to look like, well, sorry. It is difficult with this pen to draw anything, but man, that's bad. Can I erase it? I'd like to start over there. Yeah, let's try this again. So the OTA is going to attenuate the light near the edge of the frame. So you'll have a region in the center that's relatively flat, And the OTA, not as many photons get to the center, to the edge of the field as in the center, just because there's stuff in the way. There are apertures, as we call them. There's internal apertures that block some of the photons from getting to the edge. So here's the edge of the field, right? That's O. That's our OTA function. OTA. Or often we call it the optical transfer function or whatever. That's this guy. The background we can take as being uniform illumination of the skylight. And now the stray light I talked about. Now, what's this guy? Well, this guy is the quantum efficiency of the system, of the camera. So I'm sure you've all seen this. This is QE. I could have written it as QE. I should have probably, but we also call it the gain of the system. And if this is, 400 nanometers, so the visual spectrum from 400 to 700, the QE often goes up and then goes back down. And this extends all the way for silicon, all the way out to about a micron. So this might have a peak QE of 80% and so forth. Depends on the camera. Again, CMOS is unbelievably good. These guys have kind of totally nailed it, right? So that's this guy. That's the thing that turns photons into photoelectrons, because we measure photoelectrons. And then we'd like to get rid of course, all of this garbage, because this is just in the way of measuring the rest of this. So what I do is I have to take the image, I have to subtract the what we call the dark. This is dark subtraction. So if you can take darks that are the same length of time, exposure time, as the image, then this whole thing just collapses to one thing. You can just subtract this as the dark. However, if your image has a different exposure time than your dark library, say, then you've got to take biases and you've got to scale your darks to the correct amount of time that the exposure time was taken for the image. Calais, did that make any sense?
Yes. So the bias could be taken with a super short exposure that is kind of approximately zero. Like, how in practice would you get that zero exposure?
There's often a setting in the camera software to take a bias. If not, then you just set the exposure time to zero, and that'll be the shortest possible exposure that the camera will take.
Okay.
So suppose you're
then-
doing photometry of a field of stars and you're taking fairly long exposures, like a minute or so. So the shortest time the camera can expose for is, say, a millisecond. It's typical for the CMOS cameras. So a millisecond out of 10,000 milliseconds or 100,000 milliseconds isn't going to change this equation at all. So we can live with the shortest possible exposure time of the camera, and we call that the bias. Now, where does the bias come from? Well, there's just sources of bias. We're actually trying to measure individual electrons. And so the balance of the amplifier, it's a DC system. It's it requires, it's a DC voltage that's on the capacitor. You actually measure individual electron. It's more complicated. You measure charge, but it's quite complicated. But you have to first balance the amplifier every time before you start to read it out, and there can be a little bit of difference. There can be a few electrons difference, or there can be amplifiers that are not performing perfectly. There's 100 million of these amplifiers. And so, a lot of things can happen. So there can be hot pixels and so forth. So that's why we get rid of so without any exposure time at all, there can be significant bias, and we have to get rid of that. And then the dark current is just, there's defects in the silicon substrate itself. And through those defects, electrons are leaking into the charge gate, into the gate where we're accumulating the charge. And that happens at a constant rate on the average. And so we have to remove that too. If you can, as I said, if you can take a dark, which is both of these things combined, if you can take a dark frame that has the same time as the image, then you don't have to go through any of this. You just subtract it from the image and you're done. However, it's a little more complicated than that, because you want to make that a very low noise process. You only want the average of this. You don't want an individual occurrence of it, because we know an individual occurrence is going to have a lot of noise to it, because this is a process at the quantum level, and it's going to be full of noise. So what I usually do is I take, 20 darks and average them all together. And that reduces the noise power by a factor of 20, or the noise amplitude by a factor of square root of 20. Okay.
And then you scale up the time to match the image exposure time.
Well, if I have the ability to take darks, suppose this image is a 1 minute, or let's make it 100 seconds.
Mhm.
My image is 100 seconds. If I can take darks that are 100 seconds long and average 20 of those, then all I have to do is average 20 of those and to subtract it from the image. And I get the rest of this stuff, which I'm interested in.
I see. And
If
that
not-
sort of incorporates the bias in.
Yeah, that incorporates, because every dark has the bias in it that you take.
Gotcha. So under what circumstances would you want a bias to be done separately from that? Because that sort of seems like the ideal way to do it.
It is the ideal way to do it. So if you don't, suppose you're using somebody's dark library and you don't have a 100-second dark. Maybe you have a 30-second dark. So what you do is you have to have biases and your 30-second darks. And now,
I see.
and now you go through a little bit of linear mathematics, and you just scale up your 30-second darks and make them look like they were 100-second darks.
Got it. I understand. That makes total sense. And then the flats, where would the flats fit in this?
Right.
vision?
Right. The flats are to remove the OTA, to remove this curve. So suppose you have this curve, and and this could be as little as maybe 50% of the photons from here, but you've got a nice reference star that you want to use, say here. So you got a reference star here. And you might have a reference star here. So this star is only capturing 80. So the camera is only capturing, say, 80% of the light from that reference star, and maybe only, 70% here. So that would be a disaster if you wanted to use those as calibration stars, right? And your target star is right here at 100%. So we got to get rid of that problem too. So we take flats to determine what this function looks like across the field of view in X and Y. And by dividing, so I take the flat. Oh, here's my flat. And I'm going to, so I get a certain number of counts here, like 1,000 counts. And I'm measuring, twilight background. Actually, I might go to 10,000. And over here in the corner, I'm only getting 7,000 counts.
Mhm.
So I want to take my image after I've dark subtracted it, and I want to multiply it by the inverse of this, or I want to divide basically by this, right? So I'm going to normalize that and call this 1 in the center, and I'm going to call this 0.7 at the edge.
Mhm.
And so I'm going to divide by 0.7, or I'm going to multiply by 1.4. Right? So at the corner, I'd have to multiply by 1.4. And that's going to bring this to be flat.
Got it. Now, so this is all in the optics. And there's another problem that I've read about that I have thought flats were addressing, but it doesn't sound like they are, which is if your camera responds to light in a nonlinear way. So
Mhm.
that's not accounted for here. That would need to be accounted for elsewhere. Is that right?
I haven't accounted for it nicely in this equation, but it's there.
Oh, okay.
This OTA function is not just the OTA, but this O function, I'm going to add the individual pixel gain of the camera. And unfortunately, I'm going to use G again, but I'll call it GP. So every one of the pixels on this camera has a slightly different one of these.
Mhm.
So I could make this a function of X and Y, which I should have done in the first place, and then I'll be safe. Okay.
Oh, okay.
So what I'm trying to do is to know what the product of this G is times this O, and that's over here. So I should have made this a product. Just a normal product. This is a function of X and Y. And it's the gain of each individual pixel.
I see.
And this is a function of X and Y. And this is the optical transfer function through the optical system.
I see. And then
So
could G of X and Y also be a function of the light intensity itself?
yeah, that's a nonlinear thing that is much harder to deal with. So we can talk about that in a sec. But if I now magnify a region here, let's magnify that. I don't see just this smooth slope from the OTA because I've multiplied it by the pixel gain. So what I would see is I would see the same general shape, but I'd see a lot of structure to it like that. And that's the individual gain of each of the pixels, right?
Mhm.
So I'm seeing the overall behavior of the OTA, which is this smooth function here. And then I see this noisy little addition on top of it, which is the individual gain of each pixel. So I wouldn't get exactly 0.7 in the corner. I'd get 0.7 times a little bit more or a little bit less for each of the surrounding pixels because the camera gain of the pixel isn't the same.
Okay.
So now you see that when I take a flat, I'm going to get this times this. I wish I had used a better nomenclature, but you get what you get. So, okay, I get this, which is a function of X, Y, and wavelength. I get this, which is a function of X, Y, and to some degree also a function of wavelength. That's just the way optics works. Because at different wavelengths, I can have different reflectivities for mirrors. I can have different transmissions for lenses and so forth. Okay.
Mhm.
Also, part of the OTA function is all of that nasty stuff you see on a flat, which is it gives you the donuts. And
Yeah.
where do the donuts come from? Well, I've got a filter here and I've got the sensor down here. So this is what's actually collecting the light. The filter is a piece of glass with a coating on it and with dust spots and other pieces of junk on it. So where there's a dust spot, it obscures the light coming in. So here's rays of light that are coming in from, from a part of the OTA. And that spot of dust blocks some of the light, but it gets defocused in that same F ratio. And so you get a little depression in the light curve right there because of that spot of dust.
Mhm.
So this also contains all of the dusty garbage and, nasty stuff that's on your mirror or your corrector lenses or whatever. That's all there. That's there. It's all present in the flat, and we're going to divide it all out and get this nice, perfect flat curve, right? So we flat fielded it by doing that. Now, again, it's not perfect because of noise. So I have to take not just one flat, but I've got to take a bunch of them and average them together in an intelligent way to be able to use it with the lowest possible noise.
Okay. And to what extent would a flat depend on exposure time? Would it be also necessary to have the exposure time of the flat the same as the science image?
No, because it's a completely different process and it gets normalized. We're not going to care about the total number of photoelectrons we received here because it's arbitrary.
Right, I see.
As long as I haven't
Scale-
saturated the camera, I'm okay.
That makes sense, because like whatever it is we're getting, we're gonna multiply by 1.4, right? And that,
Right.
like in the corner, and that doesn't depend on exposure time. Okay, I get it. That makes sense.
Now, nonlinearities in the camera are quite a big problem. Imagine that this process isn't linear, converting photons to electrons. Suppose that at 10,000 counts, at 10,000 photons, I only get 9,000 electrons. But at 7,000 photons, I get 7,000 electrons. Now my flats are wrong by 10%, right? So when I try to flat field it, what do I get? I think too much in the center, right? I mean, if I flat fielded it, I'd be dividing by only 9,000 instead of 10,000. So my flat, which should be a straight line here, would actually be, some curve that looked like that, which would be bad again. So you've got to keep the camera out of saturation. So what we usually do is we make a little curve first and we change the exposure time, T, and we have a constant light source we're looking at. This is usually done in a laboratory, not in the field, because in the field, it's not so constant with time. And it's much harder to measure. So in the laboratory, we set up a stable light source. An LED with a constant current source is an excellent stable light source, as long as the temperature is constant. So you let it all warm up and then you start taking measurements. So you take measurements. And what you see is it doesn't keep going up, it saturates. So it'll be nice and linear at first. Yeah, try to draw a straight line with a mouse. So nice and linear. And then it'll go, it'll saturate. Sorry about that, but you get the idea. This is a straight line here. And so you want to make sure that somebody has done this, the camera manufacturer, or you do it yourself or whatever. And you want to find a point where you start to saturate the camera. The time doesn't make any difference because it's just the total number of photons. I'm just using the time to change the number of photons that got into the system. This is the point at which you want to stop accumulating photons, and there'll be a certain number of photoelectrons, right? So, and we'll call that S for saturation. So you don't want to exceed that. If you do, you won't get a good flat. You'll get a flat that has some nasty stuff to it.
I think we ran into this problem, well, I know we ran into this problem, but it was even more extreme with some Las Cumbres observations we were using because we were trying to do pulsations over multiple days. And because Las Cumbres uses different telescopes for different times, and I'm pretty sure this is the problem, the cameras had different nonlinear responses to brightness. So we got all this aliasing where it looked like we had pulsations that were a period of one day.
Right.
Because the different cameras were imaging the same cluster, and the only way we could fix it was to choose reference stars that were exactly the same brightness as each individual target, which was a huge pain. But I can see where that would fix it, because as long as you have a reference star that's exactly at that same stimulation point of the camera, that was so frustrating and hard to fix. So this explanation is really helpful because I think I kind of understand more what was going on now.
Well, let me tell you a way that I've fixed this problem to some degree. In the 20 or 25 years ago, the CCD cameras were pretty bad. They had mechanisms, they had pretty strong mechanisms for nonlinear behavior. I wonder if I can change, yeah, let me see, format. All right, that looks like a pretty color. So the CCD cameras would look like, oh man, sorry. They'd have a pretty strong, nonlinear behavior. Well, if you measure that nonlinear behavior, you can actually remove it just like you would remove anything else. You multiply by the inverse, or you divide by this curve. So if you know the curve, you know the nonlinearity as a function of the total number of photoelectrons, you just remove it pixel by pixel, just like you do everything else. And if you've got two different cameras involved, you'd have to have the two different curves. You'd have to know the two different curves, and you remove the nonlinearity from each camera individually using its own curve.
That makes sense. Yeah, LCO still has CCDs, I think. So that might have been part of it. Anyway, this is amazing. Thank you. I'm screenshotting this whiteboard in all its glory as well. And I very much appreciate thorough explanations.
That's truly a horrible slide. A dyslexic person with their left hand. I'm sorry, but I wish I had one of those graphics pads. They used to make them. Probably still buy them.
Well, we'll have
Okay.
the recording too, so
Okay.
we need to go back.
Back in the 90s, I built a cookbook camera with a friend of mine, Bob Jones, and we did them together. And Richard Berry had written a really good book about CCD cameras and photometry and photography, and we went through that process. And this is like a trip down memory lane, all the details that we went through to see, the camera behavior. And it's true that those cameras were really terrible by today's standards.
Oh man.
But they
Right.
still worked if you were careful.
They still work. I used an ST4, if you remember
Yeah.
what that was. Yeah, it was a fun camera, but it had all of these problems too.
Yeah.
Anything else, Calais, from this? That you
I think this answered my questions. I'm gonna probably watch the recording once more, but I have my screenshot. I've been taking notes and this is super helpful. So thank you so much for spending the time on it.
Well, yeah, this is a
Message.
super important, this is science. This is the sausage making of science. So you
Yeah,
have to
no,
know-
for sure. And I think it's just useful to realize all these things. Like I had a few projects in years past in which students wanted to, there was one where they were going to try and image an exoplanet, but it was below the noise floor of the observations and like just
Mhm.
and they kept on wanting to do it and they were like, oh no, we'll get some more images, and I was like, it's not gonna help because
Right.
no matter how many images you get, you can't see the signal
Yeah,
if it's
You're overcome with noise usually.
right. So just kind of having this, I think this is gonna certainly augment those discussions. And I just messaged Leon, but haven't heard back from him yet. Or I did a while ago to ask whether his conflict was every week or just this week. So we will work something out. This is my first week of school. And so from here on out, I actually have a class 11 to 12:15 and then 12:15 to 1:30. So my middle of the day is kind of out, but I could do after 1:30 or before 11. So I'm hoping we can find a time where Leon can make it too. Thanks.
So on another subject entirely, I'm thinking about having a photo center astrometry star party at my place in the desert. And October is the best month. Anybody interested in trying to make it?
Yes, very much so.
Yes.
And instead
Me
of doing
too.
astrometry, we'll be doing gold mining, gold prospecting. We'll be taking pictures of petroglyphs that are untouched. We'll be doing some collecting of UV fluorescent rocks and so forth.
Ooh, fun.
And we'll call it. And Russ will have a workshop on photo center astrometry so that it's not a complete goof off.
Dave, could we come in a motorhome?
Of course, in
place to
fact,
park?
that's even better. I have enough room I can sleep about, what, Russ, about 2 in the observatory, I don't know, 6 or 8 people comfortably.
How many miles of dirt road
In what sense?
to get to your place?
I mean, there's thousands of miles of dirt road around the place, but to get there, dirt road. Well, it's all kind of two-wheel drive dirt road unless there's been a, terrible rainstorm and
Okay.
something got washed out. So you really don't have to worry. You can get,
A motorhome would
Almost-
make it, huh?
I wouldn't take a Lamborghini in there, but aside from, or maybe a Miata either. But other than that, so is there any weekend in particular? I'm going to be there the 5th of October. I'll be back in LA. So any particular weekend would sound good?
I have all of them. I have something the first weekend, but it sounds like you're not there yet anyway. And Halloween would probably be one to not miss because but other than that, my weekends are all free.
Let me see, what Halloween is what?
I'm
last-
good the weekend of the 16th and also the 17th and also the 23rd, 24th. Kind of the
Well,
middle
how
of
about
October.
October is a great month, but I think probably the 16th and the 17th is the sweet spot.
That's pretty close to full moon.
What,
Is
do we
that a
care?
problem?
I mean,
Depends what we're
yeah,
doing.
I mean, it's nice that dark moon is, because I have a little 6-inch handheld Newtonian that I made, I don't even know how many years ago, 25 years ago. And it's fun. It's really super fun to scan the Milky Way, which we should still have in October, right? Early in the evening anyway.
How about the 9th and 10th? Is that too early?
Let me think. I get back on the 5th. I can probably manage that.
Then we'd have a nice crescent moon in the evening.
What's the new, the new moon is incredible.
New moon is the 6th.
That's kind of
Uh,
early for me. It might work. What about the 23rd, 24th?
23rd, 24th works for me, for sure.
Yeah, that's okay for me.
Yeah,
Is that past the full moon?
Yeah, it's 3 or 4 days past the full moon.
So
That's
it's,
enough.
that's good enough because, let's the 23rd, 24th.
right.
Let
And
me get an idea of how many people want to come and how many motorhomes do you have?
I think that sounds really fun. I need to check and make sure I can get away, but so far there's nothing. I'm putting it on the calendar now so that
It
so
gets
that I
blocked in. huh?
right of first refusal.
Right.
Yeah, we have a few complicating factors. I'll have to check into it and see whether I could make it or not.
All right, well, there's no rush, but I can sleep probably 8 people. And then if you bring a RV of some kind, then that's even better.
I can make it that weekend and I've got an RV, so I'm,
Wow, right. So we could have a real honest to God party out there. The Mojave Desert Photo Center Astrometry Workshop.
right.
How long does it take to get there?
For you, a long
Yeah.
time from
Long time.
What are the coordinates?
I can pass all that information. I can show you on Google Earth where it is, maybe.
What's the nearest town to the south?
There are no towns that are near.
Oh, well, there's that little railroad station.
Los Angeles.
Yeah, Los
The
Angeles.
nearest significant town
Barstow
is where?
or
Prim,
Baker.
Nevada, I guess, is the closest if you had to drive, or Baker, California.
Yeah, and but to the east, what's the name of the little town with a railroad station just down the paved road?
Okay, so that's Goffs. Is that what you're talking about? Goffs along Route 66.
No, right up in the
Needles.
preserve. There's
In the
There's a-
preserve.
Yeah, so when you come out,
Well, let me show you a map. So how do I get out of Blackboard mode? Just stop sharing and get back to here. Let me bring up, right. Let me bring up Google Earth. Where is it? Google Earth Pro. There we go.
yeah, I'm toying with the idea of driving my Miata. Might not be able to drive it the last couple of miles, but
Well, I could go pick you up somewhere. so-
yeah, exactly.
Is
All
there a
right.
phone?
You know,
Is
it'd
there
be
cell
top
phone
down
service?
weather and, you know, take kind of a circular route.
Well,
Is there
So-
cell coverage out there?
no,
No, I didn't think so.
that's the best part of the
Yeah.
place.
Yeah, real plus.
Whoa. I've forgotten how to use this version of Google Earth. So there we are, north, south. I guess that's Los Angeles. Turn on.
Looks, Baker looks almost closer to Las Vegas.
Well, we'll show you where we are. Okay. So between 40 and 15 is the Mojave National Preserve. So this is the area of the preserve. 15, there's Baker. It might have been easier just in regular old Google Maps this, but I kind of enjoy Google Earth. But it could have been a mistake.
Yeah, the town I think I was thinking was Kelso.
Yeah, Kelso, right. Okay, Kelso. We can search for Kelso.
That would come up, you know, probably along 40 west of Needles and then turn up through Kelso.
Uh-oh. That didn't work. Let's get out of this and go to Google Maps. Huh? No. Dave, what are you doing?
Kelso would take me 8 hours to drive from Mountain View. That's sort of far. I'm gonna check Las Vegas to Kelso because I could fly, I think, to Las Vegas easily.
If you can fly to Las Vegas, we can arrange a group pickup from Las Vegas.
I've flown into Las Vegas several times, and Dan Gray would fly down from Portland, Oregon, and then we would go together. You would rent a car and we'd go in together.
Yeah, we might
worked
even
well.
get Dan to come too, you know?
Yeah, we'll twist his arm firmly.
Oh, that's
Yeah, that
Medellin.
says only an hour and a half.
Medellin is in a river valley, and this is about a 3,000 foot change in elevation from the valley. It's almost 4,000 feet, so you get the idea. Anyway, let's go to Kelso, California. So here's the preserve. Kelso's kind of in the middle of it. I am in the New York mountains. And if I go to satellite view, I have to get, there it is. All right. So the elevation is 5,500 feet. So in October, it's going to be chilly, but not cold. You know, I mean, it's going to be reasonably nice weather. And there's what my friends call this Roweville. And Roweville is a cabin. a bunkhouse kind of a thingy, and an observatory with no telescope in it right now. And may probably never, because there's no internet out here. There's no cell coverage or anything. So there's some dirt road, but it's not, too bad. There's a few miles of dirt road. And if we zoom out, the stuff around this, Las Vegas is up here. There's Lake Mead and so forth. Las Vegas. Needles, which is probably the nearest place to buy groceries, or Baker for gasoline. Barstow, you may have heard of, and so forth. And there's where we are relative to the rest of the world. So it's a 250-mile drive from Los Angeles for me. And from San Diego, it's probably adds another, 50 miles to that. So you can imagine it's about a 300-mile drive.
Yeah,
Okay, well, that would be fun.
that'd be fun.
Yeah.
And so we can stay, you can stay as long as you like, but the plan would be a little bit of whatever you want to do. But I love to do the UV rocks at night. It's incredible. Quite a magical experience. Let's see. There's petroglyphs, there's mines like everywhere. We'll do a little prospecting, maybe, if I can get my act together on that, and talk about
Have you-
astrometry.
You have UV scorpions at night too?
Oh, do we ever? Like,
Oh, boy.
yeah, I've only been stung once, and it was less than a bee sting. So, yeah, not bad. Okay,
Right.
that kind of wraps
Sounds
it
like
up for
fun.
today. Sorry for the diverse.
No,
Russ,
this is
you have
great.
anything else to say?
Yeah,
Oh,
no,
so we ought to check with Dan, see what weekend would work for him.
Yeah, but I think we need to nail it down and just ask him if it works for him. It's a
Sure,
long
that
way
would work.
off, so,
Leon just got back to me a second ago on the messaging, and he said there will be an increase of times in the next year where I can't attend with that scheduling, but I still will be able to regularly attend. So,
okay.
Okay.
So the consensus is we'll leave it the time alone for right now, so we can get together Thursday at 8:30 California time, PDT.
Sounds good.
sounds good.
Okay.
All right.
Awesome.
So
And
I'll send
and
it out
Russ will-
next week.
sorry, Pat?
No, I would say I'll send it out that way for next week, and let's keep it
Oh.
going that way. Yeah.
Say those dates again, Dave.
The 20th, well, let me take a
23rd and
look.
4th, 23 and 24 is what we
And
have.
I'll probably be out there for at least 3 nights. So let me see what we got here. October. I'll probably leave Friday morning. And I'll be out there the nights of the 22nd, 23rd, and 24th, which is a Sunday. And in fact, we could make it Thursday night, Friday night, and Saturday night, if that works better for people.
I won't be able to miss Thursday school, but
What would you be able to make, Calais?
probably just the weekend, because of the school schedule. I could I'm thinking I need to do a lot of investigating to see if it could happen, but I'm thinking what the plan might be best is to fly to Las Vegas on Friday afternoon, and then drive from there, arriving probably late-ish Friday night. And then
Yeah, I'll pick everybody up, or Dan will, or whatever. We'll try to make it, or whatever you need. So I'll pick you up Friday afternoon or evening in Las Vegas, and we'll drive back out.
yeah, that would be great. We also, I'm assuming that our current Delta surge is going to be under control by then, but it seems to sort of be heading that way, maybe, hopefully. And I'm all vaccinated, so hopefully it won't.
Yeah, I'm completely vaccinated. I'm sure everybody else here.
Yeah.
Do we have any anti-vaxxers with us?
Yeah.
Stay
Russ
home.
has had 3, and he'll probably have a 4th one before he comes. So
Yeah.
he's running around to every CVS in Arizona asking for a vaccine.
For another booster. Yeah. 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 Well, hopefully all that'll be under control, but I mean, according to my calendar, I'm free that weekend. And so I just put it on there, and I think it could work.
All right, good. We'll talk about it next week. And if we have some conflicts, maybe we can adjust the schedule too. So,
Sounds
Yeah.
good.
I'm gonna just fly into Las Vegas. I'm gonna skip the Miata.
yeah, I would skip the Miata. I'll pick you up, Russ, if Dan can't make it. I'll pick you up. Okay.
Yeah, that's all great.
Awesome. Ooh, I'm excited.
This is fun. This sounds great.
Yeah. Okay. Well, I'll
All
see you all
right.
next week then.
All right, good.
Yep.
All right.
See you
Okay.
next week. Bye-bye.
Alrighty.
Bye, everybody.
Okay.
What?